patients, just to give them that opportunity as well. Today we have 3 great speakers, but before that, some of the house rules. So we ask you to just be muted during the presentations. And then after each presentation, the presentation will be about 10-15 minutes. So we'll have 5 to 10 minutes of question time afterwards. You can put your questions either in the chat or just raise your hand. And then once you want to ask your question, just switch on your camera and microphone so we can see who's actually asking the question. That out of the way, our first speaker is Martin Oberascher, who is going to do his presentation on the large-scale implementation of smart rainwater harvesting units and their effect on urban drainage networks. So Martin, over to you.
Okay, then thanks, Job, also for the introduction and for the opportunity to present my research about smart rain bells at this webinar. So my name is Martin Oberascher and I'm a researcher at the University of Innsbruck. Okay. So the Internet of Things concept includes low-cost sensors and also innovative communication technology, and thereby allowing the development and implementation of communicating items into the existing infrastructure. As a result, new possibilities for the management of urban water infrastructure are emerging. This development is particularly noticeable in the development of smart rainwater tanks and also smart rainwater harvesting. For example, the storage volume can be emptied before rain events by using real-time control technology and weather forecast to increase the detention volume. In this context, we also introduced the smart rain bell concept as an IoT-based microstorage for advanced rainwater harvesting. The smart rain bell consists of a conventional rain bell with storage volumes between 200 and 500 liters and is extended by a remotely controllable discharge valve. Measurement data and control commands are transmitted via the low power wide area network LoRa. So the main goal of the smart rain bell is to provide rainwater to substitute drinking water for irrigation purposes, but also to increase the detention volume. The aim of this work is first to evaluate the performance of a large-scale implementation of the smart bells on urban water infrastructure, and second, also to investigate the relevant factors which influences their performance. As a case study, we used an alpine municipality in Austria and retrofitted it with smart rain bells in a model-based approach. In total, we identified 384 properties where smart rain bells can be installed, and 100% of degree of penetration corresponds to 181 cubic meter additional storage volumes. And we got precipitation data in 1 minute interval and also weather forecasts in 15-minute steps for the next 24 hours from a nearby weather stations. For the simulations, we used the open source software Smartin, which was developed by our working group and can model and simulate smart rainwater harvesting systems in a coupled model of drainage and water distribution network. A key element of the control strategies are the high resolution weather forecasts, and we use the predicted rainfall to estimate the inflow into each smart rain bell, and if the inflow exceeds the available detention volume, each discharge valve is opened. The first results showed that a large-scale implementation of smart rain bells can clearly improve the integrated system performance by providing a sufficient amount of rainwater to substitute drinking water and also to reduce the CSO overflow volume. During our investigation, we had varied the forecast period between 1 hour and 12th hour, and also compared perfect and real weather forecasts. Interesting is that the 1 hour and real weather forecast showed the least improvements in terms of overflow volume. This can be explained that we used a simplified control strategy in which all the discharge valves are opened at the same time, which creates an artificial runoff wave. And if the CSO volume is already filled, then an additional event happens. In the next step, so we decided to improve the control strategies, and we compared 4 control strategies. First is all like before, as the discharge valves are opened at the same time. The second control strategy is grouped, in which we group the smart drain bells into 4 groups and which are staggered emptied. In the next strategy, CSO depth, we include the actual filling depth in the CSO structure to open the discharge valves. And in the last control strategy, MPC, we optimize the number of discharge valves which are opened to avoid this artificial CSO events. I want to show the impacts of each control strategy by using a real rain event, which is frequently interrupted by rain breaks. And during the investigated period, the CSO structure here on the right side is not completely emptied. If the filling depth is above 2.3 meter, there's an overflow. And we have one CSO vent in the morning, a bigger one, and a smaller one in the afternoon. As another reference, we also compared it with the uncontrolled rain bells. So first, with start of precipitation, the smart rain bells the uncontrolled are filled, which reduce the first runoff wave and also first peak in the CSO structure. Then the next control strategy is the smart rain bell all, and 2 events are important. First, as rain is forecasted, the smart rain bells are emptied at the beginning, which also induce a small runoff peak at the beginning. And second are the overflow peaks, which are approximately twice as high compared to the reference state. The control strategy with the least improvements is smart rain bell grouped, as they can avoid the additional discharge peaks, but through the staggered emptied, they are also slower emptying, and which decreases the performance. The control strategies with the best performance are CSO depth and MPC, both including or depending on the actual filling level or system states of the CSO structure. But our analysis also showed that these 2 control strategies are more affected by the future weather development and also the quality of the weather forecasts. So in here, because the CSO depth is below 2 meters or 2.3 meter, there is no discharge. And in the following, we have a higher filling in the afternoon, which also increases the second CSO event. And because of the quality of the weather forecast or errors in the weather forecast, there's also an additional CSO event in the afternoon. So based on these findings, we decided also to investigate the performance of the digital components of the smart rain bells in the next work. So when thinking about the smart rain bells, we identified 2 components. The first is the reliability of data communications. For the smart rain bells, we use LoRa, which operates in the public frequency range, and the transmission losses are depending on the network loads. So we have three scenarios. The first one is with low package losses. The second one is with average package losses. And the third one is with high package losses. And the second component is the quality of the weather forecasts. And for the simulations, we increased and decreased the amount of precipitation by 25%. When combining the data communications and also the weather forecasts with the control strategies, the integrated system performance gets much complexer, and I just want to highlight the main findings of this work in this presentation. So in the top, there is the performance of the CSO structure, and below we have the amount of rainwater harvesting. So first of all, as already mentioned before, the control strategy has a big influence on the performance, and for the CSO volume, the coordinated control strategy has an advantage over the uncoordinated control strategy. But when you compare or have a look at the rainwater harvesting, there are only little difference noticeable. The second is that the performance is also strongly depending on the considered scenario and also on the subsystem or either CSO or rainwater harvesting. For example, we have here, I want to discuss this control strategy CSO depth. Then we have low packet losses and also an increased precipitation, which means that we can provide more additional detention volume. And when looking at the two systems, first for the CSO, we have the best performance, but for the rainwater harvesting, this scenario combination has one of the worst performance or provides the lowest volume of rainwater for irrigation. And third, in this figure, the hatches indicate all the simulated scenarios and also in comparison with the uncontrolled rainfalls. And as you can see, it needs a careful implementation and also of the smart rainwater harvesting, also in combination with the existing infrastructure to provide an advantage over uncontrolled but often used rainwater harvesting systems. To conclude my presentation, so yes, smart rainwater harvesting can improve the integrated system performance, but at first, advanced control strategies should be preferred as they reduce the risk of artificial runoff waves and also CSO events, and the performance is also strongly depending on the digital parameters. In our case, we have the quality of the weather forecast and also the reliability of data communication, as these uncertainties can reduce the performance increases compared to the uncontrolled rain barrels. This is the end of my presentation. So thank you for your attention, and I'm looking forward to an interesting discussion.
Thanks, Martin. That was very interesting. I have a question myself. You showed that behavior of your controllers.
Yes.
Was that based on perfect? That was based on unperfect forecast, right? On
no,
real
this
forecasts.
Was real. So on the real weather forecasts.
Okay.
So
and do you see a difference in the behavior, or like that you can explain when you use perfect forecast?
So yeah, so in this example, so we use the real weather forecast, so they have errors. And when we simulate the same event with the perfect weather forecast, so in the afternoon around 15 or 3 p.m., we have 2 additional CSO events for CSO depth and model predictive control. And when we use the perfect weather forecasts, we don't have these events.
Okay, that's very interesting, and I think a very, very important conclusion as well. Just a reminder to everybody listening as well, if you have a question, just raise your hand or put it in the chat. Another question I also had is this MPC, because you have that tension between minimizing overflow and using it as water, as irrigation. So what is your objective function exactly that you use?
So in this case, we only looked at the CSO event. So because when we also include the irrigation or rainwater harvesting, it gets much more complex. And
but also more interesting, I would say, no?
Yes, but it's two different objectives. First, for the CSO, it would be beneficial when the storage volumes are always empty, and for the rainwater harvesting, it's would be good when the storage volume would be always fully filled. And because we with the weather forecasts, we empty the rain bells before the precipitation events, and because of the errors, and then the rain bells are not fully filled at the end, and then we decrease the performance, rainwater harvesting performance. So.
It makes sense. Nadia, you had a question.
Yes, I have two actually. I hope that's okay. So the first is also related to what you're showing here, and you also mentioned that you have this for the MPC scenario, the rain barrel volume doesn't decrease like the others around 12.
Yes.
I was just curious if you tried to implement an additional key in your objective function that makes it decrease, that it should target a filling degree of, what do I know, 50% or 0, or so that you force it down.
Yeah. One question, so to understand. So you mean why we don't empty the rain barrels around 12 or 11? Yeah, because the CSO depth is already, or the CSO structure is nearly filled. And when we would empty the rain barrels, we would create an additional impact, and then we would increase the CSO volume.
Okay. Okay, I see that. And then my second question was if you have considered trying to make like a test run where you change your objective function depending on kind of the state of the system. So if you forecast that you think now we will have issues with CSO, then you start emptying the system, and otherwise, so that's the objective function you use there. And when there's no CSO forecasted, then you change to another objective function, which is the rainwater harvesting one.
Yes. Good question. So it's difficult to come also because they have different objectives or different goals, and it's not so easy to combine them into one strategy.
No. So that's why I thought maybe you could make two different ones, just like depending on something, you either used one or kind of the other.
Yeah, no, good idea.
Maybe for some future research. CMAC, I'm not sure your name, but it says CMAC here.
Yes, hello. My name is Matthias Uhl from Münster University of Applied Sciences. And thank you, Martin, for this very interesting presentation. And I would like to ask the following question. We know from real-time control experiments in different sizes that you can also cause damages which wouldn't have been existed when you do not do real-time control. So in any case, there's a question of liability for possible malfunctions and damages like flooding or whatever. How do you secure that your software or your system is at least robust against this?
Thank you for the question. So when looking at the smart rain bells, the smart rain bells would be connected via rain collectors to the drainage pipe, and then it would act like connected vessels. So meaning when the smart rain bell is fully filled, then we don't have any inflow to the rain bell anymore. So this would be for malfunction at the household scale, and for malfunctions. Yes, so it's the case with the CSO structure. It would be similar, because when we don't coordinate our control strategy with the overall system states, then we create an artificial runoff wave, which could also lead to floodings. So, but our focus in this work, and also because it's a model-based approach, was more on CSO performance. But yeah, of course, when you go into reality, it would be important to avoid this situation, or to have some strategies to that these events don't happen.
I think that also ties in with Niels's question as the last question for you today, Martin, is have you piloted the solution in the real urban environment? And if not, which you sort of hinted to, is that in the planning?
Yeah, so we have one smart rain well at our campus. So it's a prototype, and we are testing it at the moment. But yeah, because of it's a prototype, there are lots of errors and
lots of work to do in the future. Thanks very much, Martin. That's great. And I think if anyone has any questions, I'm sure they can ask you afterwards, or send you an email or anything.
Yeah, sure, no problem.
Excellent. Thank you very much. I also realized that I never introduced myself because I was too excited to hear the speakers. I'm Job van der Werf. I'm a PhD student at the Delft University of Technology, also researching real-time control. And I'm a young water professional representative for the JCUD, which is why I'm here today. So after that great presentation from Martin, we'll now go to Daniel from the University of Melbourne and Shenyang Institute of Surveying, Planning, Design and Research. Did I say that right?
Yep, that's perfect.
Perfect. Okay, and he's going to present this presentation on the synergies of teamwork, the coordinated control of multiple rainwater storages.
Okay, I'll just quickly share my screen. Okay, all right. Can everyone see the screen? Is that working or?
Yeah, that's perfect.
Okay, perfect. Okay. Yeah, so thanks, Job, for organizing all this, and I'm really excited to see everyone, and it's my pleasure to be here and presenting our latest research. So the presentation today is really based on a new paper that our group has just published in early this year, talking about how we could collaborate, multiple rainwater tanks together and deliver synergy benefits. So my name is Daniel, and as Job introduced, I'm currently at the Shenyang Institute of Survey, Planning, Design and Research, and I was a PhD student at the University of Melbourne. So I think Martin has given substantial background, so I'll be just quickly talk about this. And especially with this real-time control technology, more and more people in our field kind of get excited about the smart technology, how we could use this technology cope with future climate change, blah, blah, blah. And I really see this technology as a game changer because, think about all these stormwater control measures, like such as detention pond, rainwater harvest system, natural-based, SCM such as biofilters, wetlands. We are always operating this kind of static system in a rapidly changing environment. And that's kind of not fair. So with the ability of this real-time control technology, we can now operate the static system in an adaptive way, which could potentially cope with changing environment or future climate change. And that's why get all of us excited about this technology. So if everyone just maybe using your imagination, think if what's the future going to look like in our urban water management using this real-time control technology. So you might have this long-range communication network across the city and control multiple 100,000 wetland ponds, drainage network or rainwater harvesting at different scales, and let them work together, deliver a collective outcome, for example, like flooding that we always talk about, but also for rainwater harvesting, you could also supply the water at different scales, also restore what we call base flow to our urban stream and help to restore that the in-stream ecosystems. So And currently we have done a lot of efforts, especially I see a lot of experts in the participants today. We have actually done a lot of efforts to make this work. And so far, if we just talk about rainwater harvesting systems, we have done a lot of work improving these systems at the site scale. For example, like the work we've done in using this 7-day forecast to optimize each individual rainwater tanks in an optimal way. And also we have also testing a lot of effectiveness at the drainage network scale, such as Martin have just introduced his work in looking at large scales, and we have also done a quite similar work, which is in progress is under review. And if you think about all this work, we have done a lot of work at site scale, have done a lot of work testing, rule-based or MPC, optimizing individual system at the network scale. But what we didn't really investigating, or we kind of lack the efforts in investigating, is how to collaborate multiple storage as a system and deliver a synergy benefits. And what I mean about control different systems as a one integrated system is more like a teamwork, like we always do in a daily life. We work with other researchers in order to have a better research outcome, or we're playing a sport, playing a team to have a better outcome. So what's the vision of this work is really you want all different systems to work together and deliver a better outcome. So if we talk about control, you definitely want to think about what's the objectives for that control. So for our work, the urban flooding is, of course, one of the major objectives to think about for our control. But more importantly, the change to the urban streams is not just limiting to the peak flow, which leading to urban flooding, but also the loss of base flow, which is essentially leading to the stream degradation. So what do we want to do with this control is we want to have multi-objectives help to restore the entire flow regimes in our urban environment and to have a better environmental outcome. So we build a model, aiming for this kind of teamwork for a collective goal. We convert this real-time control, used to be a rule-based, into optimization model, which is essentially the model predictive control. And the control model is solved by genetic algorithm, one type of genetic algorithm. And the objectives for this optimization model is, first of all, the supply, which is normally how why we need a rainwater harvesting system. But more importantly, like I just said, is on the flooding and that environmental flow. And the figure on the left side is a conceptual representation of how the model looks like. We couple 3 different tanks together. We have different parameters in the model, and we also model how this real-time control could let these 3 tanks work together. We also compare, in the same circumstance, what's the difference between a collaborative scenario versus individual control. So the collaborative control, of course, is what's the status in other systems and how we could deliver a collective outcome. But for the individual control, it's really just optimized by itself. We don't know what's the water level in other tanks or what's the overflow for other tanks. So essentially, they work on their own. We build a range of scenarios, different combination of tank sizes, different demand and different parameters in systems in order to get a full understanding of how this collaboration kind of looks like. So here's an example on one particular event that we test through a 6.5-year time frame. So on each day, on each event, we predicted as an overflow. We calculate the value of different objective function and plot as a kind of parietal front. And we also have a preference on this, what we call a selection criteria in order to choose, all right, you have 500 sets of results. What is the one that you're going to implement in the next, in the time horizon, in the next time horizon? So the selection criteria is basically we prefer the environment floods as on the top, and also the flooding, and then we have the last preference on the supply. And here the red dot there is showing in that 500 sets of results, what's the final selection in this 500 sets of predictions. After you have an understanding of this one particular selection, we implement in the next time horizon before the whole objective function being recalculated, just like the same structure as the model predictive control. So perhaps not looking into details, but what I want to show here is we did a range of analysis across different scenarios, different control strategies. On the top figure there, the yellow one is the individual control, and the collaborative one, and the green one is the collaborative control. And all these two figures are indicating what's the performance of base flow in different scenarios. And the top at the bottom figure here showing within that particular scenarios, what's the proportion of base flow restoration in each of the tanks, because we're looking at 3 different tanks. In order to figure out where the synergy is, we have to look at, first of all, what's the overall outcome? And secondly, what's the split of tasks in different systems? So what we're showing here is this collaborative control, which is basically the green there, and also the bottom bar there, basically show they generally deliver a higher overflow base flow efficiency on the top figure. And if you look into details of the bottom figure here, the general conclusion out of these is these large storages. For example, like one tank, we assume 15 kiloliter tanks. So these large storages compensate for small underperforming systems. The benefits you can see if you look at this scenario, it's quite obvious that, if you're just looking at these guys, the 15 kiloliter tank release much more water than you compare with those 15 kiloliter tank in individual scenarios. What I want to say is the collaborative control, the big system in those collaborative control knows those small systems won't be able to give those water in time and also fit our demand. So, in compensate, they will do more heavy lifting at their side to save all these small systems. If you compare the other aspects, for example, like the supply and the retention, which is referred to the flooding performance, you basically see almost no difference compared to different MPC algorithms, so individual control and collaborative control. And of course, they deliver better retention performance compared to the no control scenarios. So after all these, what would be the next future research, after all this? Of course, because the limitation of this work, we're only looking at, multiple systems work together. But one thing we didn't explore is the routing in between. So, in the real world, the 3 tanks wouldn't be sitting together. They might be in different places in the catchment. What could potentially do in the future is, incorporating the flooding model, or maybe the hydraulic model for the drainage pipes and all that, in incorporating that into the MPC system. So then you have the ability to predict, in a certain control, what's the effect in downstreams. And also think about the implementation, because MPC is of course great, but if you have a more detailed model, internal model, then you may have a higher cost in the computational time. So if we talk about real-time implementations, would that be feasible? Would that be possible? If you think about what we define as a real time, so it could be interesting in the future to think about whether optimization-based control or rule-based control. Maybe rule-based control can deliver 95% or maybe 75%. I'm just giving a number randomly. But what I'm trying to say here is, it will be very interesting to look at, which holds the best, comprehensive benefits. Of course, you want to think about the application in other SEMs, such as the wetland, which is also one direction that our group is looking at, leading by Tim Fletcher and also Chris Salter, looking at how this technology could be used in wetland, biofilters, and other SEMs. In the end, all the thinking from my side is from the kind of a technical side. What would be the future in thinking about the social economic side? So, just using an example, like I just said, maybe I'll just get a question, in 1 minute, is, if the big tanks do the heavy lifting for the small tanks, if we implement in the future, the resident maybe say, it's not fair. Why would I do this? So there will be a range of socio-economic questions around this technology to make this technology, implementing our real life in the future. And questions?
Thanks very much, Daniel. I had a question about the design of so you have 3 tanks. Do you see a way of co-optimizing the design, like the scaling of the tanks and a sort of control? So rather than the assumption I have these 3 tanks, I should control them using both?
Yep. So the reason we go for these 3 tanks is, in the very beginning design of this work, we have tried to say 3 tanks, 4 tanks, and 5 tanks. And essentially the assumption we build on is, as long as you have more than 2 tanks, which is, sometimes the optimization, you make us kind of same results for, if you have built a 2 tank systems, and that's probably more complicated than the mathematical side is think about optimization, which I probably don't have the expertise to kind of explain. But, in the beginning design of this work, we testing, 3, 4, and 5, and we kind of figured out, the 3 tanks is, if you want to generate a general result, the 3 tanks is probably enough for the aim of this study. But of course, like I just said, in the future, you maybe want not just limiting 3 tanks, or maybe think about 4, 10, 20, or 100, which is, I see that entirely possible, because that's basically how we did in the urban drainage. You think about, different, pumps and, different control in the drainage network. The scale is much more bigger than 3. So I think in the future, we have to explore what's the effectiveness in looking at the catchment scale.
And then move away from sort of a centralized control, because obviously with 100 actuators in a system, you can never find optimal solutions.
That could be, that would be other question, because then if you're doing the centralized control for 100 systems, we have to think about, how we define as a real time, or you could use different structures, say, you group 10 tanks as a group, then as a sub-catchment or something like that. Again, this is just some thought that I had in my mind. I don't have, the kind of ability to explore during the PhD, so.
No, fair enough, but the long research life ahead of you, so plenty of time to do it anyway. If there's any other questions, then otherwise we're gonna go to Nadia soon. I don't see any. If anyone comes up with a question anyway, then we have Daniel's email address right in front of us right here. So I assume you're happy to get any questions on that. Excellent. Then we'll indeed go to Nadia. I don't think Nadia needs much of an introduction. I just remember that it really helped my start of the PhD reading your review of the 2018 MPC review, which I still use every day almost. And Nadia will bring us back to, I think, the more traditional RTC of the urban drainage system by trying to answer the question of where we stand in the way of implementation of RTC in urban drainage systems and some experiences from Denmark.
Thank you very much, Job. Can you all see my screen?
All working fine.
Perfect. Yeah, so I'll actually take us a little bit away from all the technical stuff. Currently, I'm doing an industrial postdoc in collaboration with a consultancy company called NVD and then the Technical University of Denmark. So in this postdoc, I'm also looking on some of the social stuff behind control. Yeah, so as Job also mentioned, in my PhD, I did a lot of stuff on model predictive control, advanced control, sitting there trying to code different control algorithms. And then in this postdoc, and what I also realized while doing my PhD was that there's a lot of utilities out there that's not really ready for all that advanced control. So I really felt like university and research was very far from what they actually did in practice, at least in Denmark. So in this postdoc, instead of doing some very high science, I'm more trying to look at how do we actually then get some of these concepts implemented in reality. And when I've been talking with utilities, what I hear is that they often think that going from the idea of using control, I think most of them can see the purpose of that, but then going into implementation is a little bit like climbing a really, really huge mountain. And instead, I wanted to see if we can smoothen this mountain a little bit, so it's more like walking a hill to implement the control out there in reality. Yeah, so that's the topic of my talk today, is what stands in the way for implementing RTC? Why is it that this mountain is so high, and what can we do to make it more into a small hill? So what I've done is that in my postdoc, I have 6 Danish utilities on board. These are the names, who gives me feedback along the way. So I've been working on the postdoc for now a little more than a year. And what I've been doing in the way is that I had some initial interviews individually with each utility. Then we had a workshop. Then I did some work that I'm not going to talk about today, but where I talked with all the utilities again, one-on-one. We had workshop 2, workshop 3, I just finished, and then I did a bunch of literature study as well. So that's kind of been the process so far. And what I've gathered from the literature, the interviews, and the workshops are 2 lists, one of drivers for control and one of barriers to control. So what is it really that the utilities wish to obtain with control, and what kind of hinders them from engaging with control? And I've categorized these drivers and barriers into 4 different categories. The first, I used sustainable terms, like categorized them as environmental goals, economic goals, and social goals. And then I added this extra box that's technical goals or technical objectives, which are if there's like something wrong with the technique, so there's some practicalities that stands in the way for control. So I gathered it all in these huge Excel files that I'm not going to bore you with, but I did a lot of coding in there, like trying also to see together what I found in literature, what I heard from the utilities, and then see if I could synthesize it into something that could, on a more overall level. And that's what I want to present to you today. So if we start looking at the environmental objectives, what is it that in relation to the environment that the utilities want to obtain, or that they're a little bit scared about? So I think these are obvious to most of us. So they want to reduce combined sewer overflows. That could be in terms of volumes, numbers, durations, or sometimes the loads, pollution loads that comes through CSOs. They want to optimize the operation of wastewater treatment plants. They want a better and cleaner environment that could be looking specifically at the fish species, but it could also be something like the level of oxygen in the recipients. Then they are also very happy, the utilities, about this possibility of prioritizing between different overflow structures, maybe depending on the recipient sensitivity. And then it's also written that since control is often perceived as being much faster to implement than other solutions, you also get these environmental benefits quicker. And then as a more new thing on the scene is this possibility to reduce the greenhouse gas emissions, both from the construction. There's often a lot of greenhouse gas emissions coming from when you have to construct a new basin or separate your sewer system. There's also something about that you can optimize the use of electricity, and you can also optimize the operation of your wastewater treatment plant, also with respect to greenhouse gases. Then if we look at the barriers, it's often, and that makes totally sense, it's often advised that you look at the entire integrated system at once when you try to control your system, but that is quite difficult. It is being done in literature. I don't think that it's the first step that most utilities would take. And what I hear is that people are actually afraid that if they only optimize for one part of the system, another part will be suboptimal and you'll actually just do things worse than they are today, because it is complex systems. If we go into the economic objectives, I think it makes sense also to most of us. There's of course some cost coming with planning of control. There's some cost coming with implementing actuators and SCADA systems and fail-safe systems and all this. And there's also some cost in operating the system, maintaining the sensors, etc. afterwards. But depending on the current setup of the utilities, this can actually both be a driver and a barrier. Let's say there's a utility that has most of this in place anyway, because they do maybe some very local type of controls, then it can be a driver. Hey, we already have all this stuff. But to utilities that don't have it, it could also act as a barrier. And then there's also local rules and regulations that can stand in the way to control, even though control might be a cheaper solution. If you just do the math, it might not always be the one that's actually financially most beneficial for the utility to do. Then if we go to the technical barriers, one of the things that you hear is that control is a very flexible solution. Let's say you construct a new part of the city, there are changes in regulations, or there's changes in where you want to prioritize your overflow, then control is a way that you can quickly shift your system. What the utilities say is that it's also flexible in the sense that you can quickly incorporate it and remove it again. Many of the utilities in Denmark have sewer system separation strategies, but they last some up to 100 years. And they see that control is something you could implement maybe in the meantime, and then once that your entire sewer system is separated, you can either remove it again or you can change it. There's also a lack of space in many, at least in many Danish cities, but I guess it's a global problem, for construction of basins, for instance. So here control is also seen as something where you don't need a lot of space, and then that the technology is already there, and that you can actually, as Daniel also said, maybe start rather simple. You can start with something that's rule-based and still get quite far. Barriers are that maybe there's not enough volume in your system to actually have something to store the water in. Maybe the constructions that you have are not really designed for control, or the equipment that you already installed out there is not really appropriate for real-time control, meaning that you would actually have to go out and adjust the system that you already created in order for it to function for control. And then that there is a lack of automated procedures that can tell you, is there a control potential at all? Do I have the necessary volume? And once you figure that out, then there's also a lack of either automated procedures to create the control strategies, or automated procedures or transferable concepts that you can take from one case study to the other to make the investment for the utility smaller. And then finally, we come to the topic that I think is actually one of the most interesting one, and that is the social objectives. So in the end, it's people who has to implement the control. So what do they actually see as the drivers and the barriers to control. So some of the utilities mentioned that they have a wish to be more data-driven and that they see control as an integral part of this, this journey, and that it's also something they see they can use as branding for their utility. They see it as a way to develop the skills of their employees and retain them by giving them interesting tasks also in the future. Then another driver for control is sometimes that there's external pressure on the utilities that can be either from politicians or municipalities. A couple of years ago in Denmark, we had a quite big, I would say it was kind of a media scandal. So one of the utilities were planning to let out some wastewater untreated, and the public took that up and all the media took it up. And I know that some of the directors from some of the utility companies started walking down the aisles in the utilities asking, do we also do that? And I think that pressure can also sometimes drive that you start engaging with control. Then it can also be, I would call them champions within the utility. It could be one from the planning department or somebody from the operational team who sees that there's this basin that we don't use fully. And that's where actually the control starts. It's because somebody gets a good idea to change something. And previous experience with control is also a major driver. Has somebody in the utility actually done this before? Because then it doesn't seem as difficult. Barriers can be a lack of focus, especially from upper management on reduction of overflows. It can be that nobody in the utility knows anything about control. They don't know the potential for control in their system. There's no, and that's also been pointed out, I think the last 30 years in the academic literature, there's no guidance to how do you actually implement control. And I know that there are some studies out there that tries to describe this, but I don't think we are there yet. At least it's definitely not used out in practice. And many utilities have this idea that control is something very difficult and complex. And that's also why they don't start to engage and learn about control, because they think, oh, that's going to take a lot of time and energy. And is that really worth it? Then we're missing examples of both how control behaves and performs in terms of our environmental objectives, but also in relation to economics, and especially also how do you actually make these assessments. Then there's prejudice, especially from operators against control. It's something a little bit dangerous. We normally do it like this. Now somebody else comes and tells us what to do, and we were not part of the decision-making process. That's a little bit scary. And this is very different from utility to utility. In the 6 utilities I've worked with, in some utilities, the people who are operating the system are actually also the ones that are planning it. It's very small utilities, but in other utilities, it's 2 very separate teams, sometimes sitting at 2 separate locations, and they don't collaborate very well together. They're not used to collaborate, and they actually also sometimes talk a little bit different language. When the operating teams says something, it's not always that the planning team understands what they actually means, and vice versa, and that can also hinder the uptake of control. And then there's a lot of new risks coming with control. Cybersecurity, what if we invest a lot of money and it shows that there was no potential for control in our system? What if we have power outage or one of the actuators fail? Can the operators actually still remember to operate it later on if they have to take over manually, if everything has been automated for a while? Then there's what happens if we make a temporary constructions in the area? If we have to excavate or dig up a pipe, will the remaining part of the control then still work? Will it give a higher risk of flooding? And who actually has the responsibility if something goes wrong? Is that the operator? Is that the utility? Is it a common responsibility for the utility and the municipality? Or who actually sits with this burden? And then in the end, there's time. And I think, at least in Denmark, many utilities, they are really, really, really busy. So it takes time to both find out, is there a potential, learn about control, train your personnel, plan the control, implement it, and operate it afterwards. And again, if the utility already knows a bit about control, this can be a driver because they're like, this is not much more work than what we already do today. While other utilities really, really see this as a barrier, being like, oh, all these extra things we have to do. And it's not always just possible to make a cost-benefit analysis and say, then hire 2 extra persons. That's just not how it always works out in reality. So I think we can use these drivers and barriers to really see what is it that we need to also use to sell these concepts to utilities. We have to really push the drivers and make the barriers lower, right? That's how we ensure that all the good work of the previous speakers, and there's been made so much good research out there on real-time control. And this is what we have to do to actually also bring it into practice. Then just a few final remarks about the decision-making process. I think there's a lot of things that we already do in research. We look at overflows, we look also a bit on economics, and when the Danish utilities have to prioritize it, that's also what they say is really important. The economics, however, is not something that's obvious to utilities that that's actually a driver. Some of them don't have the experience and also think of it as a barrier. Then there's all these things that we actually don't really look at. Some of them are drivers, some of them are barriers, but we don't assess them really in academia, besides that there's been a recent focus on this automation of potential estimation, and can you make strategies that you can transfer. Then I think another point is that in academia, we often think that the decision-making process is very linear. You start with a problem, you make your overflow calculations, you make a cost-benefit calculation, while in reality, it's much more complex. And also we often we say, okay, either you make control or you build basins or you separate. But in the utilities, they often have a strategy already that might be sewer system separation. And maybe it's only when one of the operators see that there's a potential that they actually look towards control. So just in the end, a few take-home messages that the decision-making process in utilities are not always as we expect them to be in academia, and that they don't see control necessarily as a solution in the same way as other types of solutions is, that there's a lot of unknowns and new ways of working related to control, which hinders the uptake, that it's often driven by champions within the utilities who sees a potential. And I think most importantly, we need to expand our research beyond just quantifying environmental and economical objectives if we really want our research to have an impact. Yes, thank you very much.
Thank you very much, Nadia. I had a question about that last thing you said. So if you can go back one slide. So the research need to expand beyond just quantifying environmental and economical objectives. What do you see the role of academia is to get this implemented in both education and research, I suppose?
Well, I think we need also to try to look at some of these other barriers that are here, for instance, how do we make good guidelines? What is the good way of implementing control? How can we deal with some of the risks that are there? Can we make it easier for utilities to make these cost-benefit analysis? Can we make it? Can we make systems for cybersecurity? Could we somehow do something? So do some calculations that could show how much extra time they would have to use. Could we be better at assessing the risk of flooding when we do research? I think there's some things that could be done there, and explained better also in the literature that we write.
Excellent. I think a lot to do for us anyway. Martin Fenkel asked about the legal barriers. Is there any legislation compatible with RTC?
I don't think so. In Denmark, at least that's what I hear from the participating utilities, is that they are unsure who has the responsibility and that there's no really guidelines for how to handle it. So I don't think there are.
And any ethical issues? Do you see any of those within the utilities, like prioritizing real time between environmental impact, economical savings? What's the objective function that we're making?
Yes, actually, that was funny. In my last workshop with the utilities, I gave them all these small dots. They have had to kind of score all the different barriers and drivers that I had found with conversations with them and in literature. And these are the barriers that were highlighted. And one I haven't shown here is that there would be an additional cost at the wastewater treatment plant when you reduce CSOs. And that was actually one that was prioritized. And I was like, hey, people, but it's a good thing that we really minimize the impact on our environment. And they were like, yeah, but we also have this economic frame we need to operate within. And if it gets more expensive to clean the water at the wastewater treatment plant because there's simply more water, then it might not always be attractive to us. So I think, at least for me, there is an ethical mismatch.
Okay, just excuse me. Yeah, I don't know how to raise my hand, so I do it like that.
Excellent. Go ahead.
Okay, Mr. Uhl was first, I guess.
No, go ahead. You.
Okay.
I saw your hand.
What Nadia just showed us is exactly what my experience is. I work for the water authorities in Germany, and we had just one project exactly similar to that what Nadia showed us, and it's very, very important for all the people in that project to take contact with the water authorities in a very early phase of such a project, just to inform them, as we say, to take them within the boat, that they know what is going on. And in that project that I give the permission, we talked about, I don't know, 2 or 3 years until we finished that project very, very well. And it's one of the best projects of controlling rainwater things I've ever had. But we had a lot of time talking to each other to declare what is the purpose and so on and so on. And that's what it's very good what Nadia showed us. Yeah, go to the authorities, inform them, talk to them, and they will say in a very, very early phase of a project, what are maybe the legal barriers, you know? It's very, very important, because in the end of that project, I gave them the permission to do it. And it was new stuff for us also. And we said, okay, we give you the permission for maybe 1 or 2 years, and then you can test your system and we will show whether it works or not. And after 2 or 3 years, they gave them the final permission to run that system. And that's very, very important. On another conference, I heard some guys of a technical studio, and they said, oh, it's like that complicated to talk with the authorities. What did they do? They are sitting in the office, they are thinking, they are calculating, they are writing sheets of paper, and then they go to the authority and said, that's it, bang. And that does not work. That's a
more proactive stance from academia is what you're arguing for.
Yes.
I think very good. Also very interesting, of course, to see the differences in between different countries.
Yeah.
I think Matthias had a question, and then I think we have to wrap up as well. So Matthias, you have the last one, and then there are some questions in the chat that maybe Nadia you can address afterwards.
Yes, thank you very much. Thank you for this very good and clear presentation. We see that it's a very complicated problem we have to solve here, affecting various factors and influencing things. And I was wondering whether you also worked about the role of emotions. That means at least the emotional relationship we have to rain. In the northern countries, very often rain is said to be ugly. In the southern, drier countries, it is a very, very good thing. So the question is, can we promote at least rain as a good factor, as a good gift from space for us people to enhance the acceptance of stormwater use?
Well, maybe, I think at least that this, and I think also actually this slide shows that most of these are colored blue, and that's all the ones that comes from the social objectives, right? That emotions are really important, and what drives people is really important. What exactly it takes, I think actually also sometimes we just in our research need to be more inviting or maybe more open to people who know something about these things, because I think most people of us who comes from very technical backgrounds are maybe not the ones who knows how to approach all of this out in reality and what it actually takes of research to combat some of these things.
I like that as a last conclusion for this this session. So I'd like to thank Nadia, Martin, and Daniel, especially for their presentations. They're great presentations. I think they've given us a lot of things to think about in the coming times, and maybe some future research directions as well. We did record this session. It will be online somewhere at some point. We're not entirely sure what we're going to do with it, but we'll see. So thanks everybody for joining, and I hope to see you in future conferences and that.
Thanks everyone. Thanks Job for organizing this. It's great.
Cheers. Thanks very much.
Cheers.